Class, in this video, we continue our discussion of section 4.2 in your textbook on the natural exponential function. At the top of page 2 of your lecture handout, we have the function f of x is equal to e to the minus 3x power, and we want to evaluate this function at x equals 1/6. So to evaluate the function x equals 1/6, we just put in 1/6 in for x on the right hand side of the equal sign, and we have f of 1/6 is equal to e to the minus 3 times 1/6 power. Minus 3 times 1/6 simplifies to minus 3/6, and minus 3/6 simplifies to minus 1/2. So f of 1/6 is equal to e to the minus 1/2 power. Well, minus 1/2 is the same as minus 0.5, and so e to the minus 0.5, using your calculator to 3 decimal places, is 0.607. Next, we want to evaluate the function at x equals minus pi. To do that, we just put in minus pi in for x up here, and we have f of minus pi is equal to e to the minus 3 times minus pi power. Minus 3 times minus pi is plus 3 pi, and again, using your calculator, e to the 3 times pi power to 3 decimal places is 12,391.648. In example 3 down here, we have a word problem involving the natural exponential function. We're told when a certain medical drug is given to a patient, the amount of the drug in milligrams in the bloodstream after t hours is given by this function. D of t is equal to 60 times e to the minus 0.4 t power. And you're asked how many milligrams of the drug remain in the bloodstream after 4 hours. So up here, t is the independent variable. And in mathematics, we often use the letter T from the alphabet to represent time. And D of T represents the amount of drug in the bloodstream after T hours. So to find how many milligrams of the drug remain in the bloodstream after 4 hours, we just evaluate the function up here at T equals 4. And when we do that, we have D of 4 is equal to 60 times e to the minus 0.4 times 4 power. Well, in the exponent, minus 0.4 times 4 is equal to minus 1.6. So this here, 60 times e to the minus 0.4 times 4 power, simplifies to 60 times e to the minus 1.6 power. And now you got to follow the order of operations, PEMDAS, right? Exponentiation comes before multiplication. Well, on your calculator, e to the minus 1.6 power is equal to 0.2019 to 4 decimal places. And then when you multiply that number by 60 and round to 1 decimal place, you get 12.1. 12.1 what? 12.1 milligrams. So after 4 hours, there are 12.1 milligrams of the drug in the bloodstream. Over here on the right is the graph of this function, d of t equals 60 times e to the minus 0.4 t power, and you can see that this is a decreasing, right? The function is decreasing. It's only graphed in the first quadrant of the xy, or the coordinate plane, right? The horizontal axis is the t-axis. The vertical axis is the y-axis, or d of t, and we only graph it for positive values of t because time can't be negative. And you can see at t equals 4, this is the point on the graph right here, at t equals 4, and the y value at t equals 4 is equal to 12.1. Now, this kind of function, where the value of the function decreases as time increases, that's called an exponential decay type function, right? This up here, d of t equals 60 times e to the minus 0.4t. That's an example of what we call an exponential decay model. As time increases, the quantity decreases. Example 4 is another example of an exponential decay model. We're given a radioactive substance decays so that the amount remaining after t days is given by the function m of t equal to 10 times e to the minus 0.017 t power. Again, t represents time. The independent variable t represent time. Represent time in days in this example. And m of t is the amount of the radioactive substance after t days. And so again, you can see the graph over here of m of the function here, m of t. As t increases, the horizontal axis is the t-axis. As time increases, the amount of the substance is decreasing. And so you can see this is another example of exponential decay. You're asked how much remains after 45 days. Well, we just put in 45 in for t up here, and we have m of 45 is equal to 10 times e to the minus 0.017 times 45 power. That minus 0.017 times 45 is equal to minus 0.765, and so this up here is equal to 10 times e to the minus 0.765 power. Again, you got the order of operations. Exponentiation comes before multiplication. So you got to calculate e to the minus 0.765 power and then multiply that by 10, and to one decimal place the amount of the radioactive substance after 45 days is 4.7 kilograms.